Learn like a pro.
All right, let's jump right in. Have you ever really thought about how we take something as basic as just moving stuff, like spinning a wheel or water falling down a dam, and turn it into the electricity that runs, well, everything? That little bit of magic is called electromagnetic induction, and that's exactly what we're going to unpack today. So, what you're seeing here, this is basically the whole puzzle in one picture. A magnet, a coil of wire, and somehow, power. Over the next few minutes, we're going to take this exact blueprint and break it down piece by piece so you understand exactly how this incredible engine really works. So where did all this start? Well, to get how we generate power on a massive scale today, we have to go all the way back to a really simple but totally game-changing experiment by the one and only Michael Faraday. What Faraday did was simple. He took a magnet and a coil of wire hooked up to a galvanometer, which is just a fancy name for a super-sensitive electricity meter. And his first discovery? The second he pushed the magnet into the coil, boom, the needle jumped. He had just created a current out of thin air. But here's the part that changed everything. He stopped. He held the magnet perfectly still right inside the coil and nothing. The current was gone. The needle just dropped right back to zero. This was huge, because it proved that just having a magnet nearby wasn't enough. Something else had to be happening. And this is the final piece of the puzzle. When he pulled the magnet back out of the coil, the needle jumped again. But wait, look closely. It deflected in the opposite direction. So not only does motion create a current, but the direction of that motion is a huge deal. So if you remember one thing from this experiment, make it this. It's all about the change. A static, unchanging magnetic field does absolutely nothing. It's the moving, the changing, the magnetic field lines cutting across the wire that does all the work. That's the trigger. Okay, so we've nailed down that a changing field creates a current. Simple enough. But the next obvious question is, how much current? A little? A lot? How do we control it? To get that answer, we need to look at the first big rule of induction, Faraday's law. Faraday's law gives us the rule for how much. And the key phrase here, the one you want to lock in, is rate of change. It's not just about how much the field changes, it's about how fast you change it. When it comes to induction, speed is everything. I love this visual because it's the perfect analogy. Think of it like a set of scales. On one side, you have the electrical power you're generating, the EMF. On the other side, you have how fast you're changing that magnetic field. And they're perfectly linked. You push the speed up, the power goes up. Simple as that. All right, we figured out the how much part of the equation, but remember how the needle went both forwards and backwards? So which way does the current actually flow? For that answer, we need our second big rule, Lenz's law. Okay, get this. Lenz's law basically says that nature is, well, kind of stubborn. It does not like change. So whatever you do to change the magnetic field, the new current you create will generate its own little magnetic field to fight you every step of the way. It's nature's way of saying, hey, I liked it the way it was. Let's watch this in action. You take a north pole of a magnet and you start pushing it towards a coil. The coil immediately fights back by creating its own north pole right at the entrance. Why? Because like poles repel. It's literally trying to push your magnet away. And once you know the coil is making a north pole, you can use a neat trick called the right-hand grip rule to find the exact direction the current is flowing. This is so cool. It shows you the law works both ways. When you push the magnet in, the coil pushes back. Repulsion. But when you try to pull the magnet out, the coil does the opposite. It flips its polarity to a south pole to try and pull the magnet back in. It fights you coming and it fights you going. It always opposes the change. So you might be asking, why is nature so argumentative? Well, it's not some quirky rule. It's something way more fundamental, the law of conservation of energy. You can't just create energy out of nothing. That pushback you feel from the coil, that's real resistance. And the physical work you have to do to overcome it, that's what's being converted from your kinetic energy into electrical energy. There's no free lunch. So we get the how and the why. Now for the fun part. How do we take these basic rules and really crank things up? How do we go from a tiny flicker to some serious power? Imagine you're sitting at a control panel. You've got 3 big levers in front of you to dial up the power. Lever 1, the number of turns in the coil. More wire means more current. Lever 2, magnetic field strength. A stronger, beefier magnet gets you more power. And lever 3, the one Faraday taught us about, speed. The faster you move things, the more juice you're going to get. Okay, let's put our new knowledge to the test. We've been talking about coils this whole time, but what happens if we simplify things way, way down? What if we just have one single straight wire? You know what? The rules don't change one bit. As that wire moves down, it's slicing right through those invisible magnetic field lines. And that cutting action? That's the change we've been talking about this whole time. And just that is enough to create a current and make that meter's needle jump. And look how beautifully our rules predict exactly what happens. You use stronger magnets, you get a bigger deflection, just like our control panel said you would. You move the wire slower and upwards, you get a smaller deflection in the opposite direction, exactly what Lenz's law predicts. And of course, if you swap that single wire back to a coil, bam, a much bigger deflection. See? It all just clicks together perfectly. So here it is, the whole shebang, the complete blueprint. On one side, you've got Faraday's law. That's your how much rule. It tells you how to get more power. On the other side, you've got Lenz's law. That's your which way rule, all driven by the conservation of energy. These two laws working together are the whole story. What's really incredible is that this same simple blueprint explains everything from a tiny spark in a lab to the massive generators that power our entire cities. The physics is exactly the same, just on an epic scale. So I'll leave you with this thought. We just saw what one little wire can do. Now imagine that wire is as thick as your arm, and instead of your hand moving it, you have an entire river pushing a massive turbine, spinning it day in and day out. The power you get from that, well, it's staggering.